So, today we are going to get all the way down to the very tiniest level of how we describe matter. And it's called matter at the atomic level. And so here is this word, the atom. And it was postulated all the way back in the days of Greek philosophy that there had to be the smallest unit of matter that maintained those properties. And so that will suffice as our definition for what an atom is. The smallest unit of matter that maintained distinct properties. So let's start off with one of the more common elements that is relevant to life as we know it. This is carbon. We will spend more time discussing what all of these numbers mean, but carbon is one of 92 elements that appear on something called the periodic table, and that looks like this. This looks like a big jumble, but it's really laid out pretty sensically, and we'll get to what all this stuff means in a little bit. Well, here's carbon right here, represented by this symbol C. And what it does is, this periodic table, is it shows us, it's actually an arrangement. It's actually laid out pretty neatly, and we'll get into the layout of it more and more as we go. But here's a quick overview of how the periodic table works and why it looks like it does. So let's make this a little bit bigger so that we can see it a bit more clearly. Now there's a couple of reasons why this is laid out the way it is. All right, we're going to break it down into two distinctions. We've got columns like this. All right, these are known as groups. Okay, and they have numbers 1, 2, 3, 4, and so on, all the way up to 18. We also have what we call periods. These are rows. There are 7 of them. They go all the way across like this. All right? There are 7 periods, and we'll learn how to refer to these later on. All right? We also notice that there is this distinction here, this flight of stairs that we're going to pay a bit more attention to this in a little bit. All right? So we've got groups and we've got periods. We'll get into more what the numbers mean in a little bit. What we're mostly concerned with is that elements that are in a group share similar properties. I'll give you a couple of examples. These guys over here, group 18, these are what we're going to call the noble gases. Let's take a closer look. So here is our group of noble gases. They're found all the way on the rightmost side of the periodic table in group 18. And there are 6 commonly recognized noble gases. They are helium, neon, argon, krypton, xenon, and radon. And if you've never heard why they're called the noble gases, It's because they are inert. In other words, they don't react with anything. There's always an exception to that rule, but for the most part, they don't react. That is their common property. They are essentially unreactive. Let's take a look at another one. This group here, this is what we call group 17. We're going to call this group the halogens. And there are 5 of these guys that we commonly recognize. They are fluorine, chlorine, bromine, iodine, and something called astatine. These guys have a common property. They are all toxic as well as highly reactive. And you're probably saying, well, where have we seen these before, Mr. O? What are you talking about? They're highly reactive and also toxic. Well, you've used at least 3 of these before somewhere in your lives. For example, you've used fluoride if you've ever gone to the dentist or brushed your teeth or used mouthwash or even had tap water, because in the state of Illinois and in the city of Chicago, we add fluoride to our tap water. So fluorine, in this case, the fluoride ion, prevents tooth decay because it eliminates the bacteria that cause it. So you've used that stuff before. Any of the others? I think you've seen a couple others. You've used chlorine if you've ever taken a swim in a pool. If you have your own pool, or if you've ever gone to a public pool, because chlorine is really good at killing the bacteria in pool water. So we use this as a disinfectant because it is really good at cleaning all that stuff out. Any other halogens that we've used before? I think you have. If you've ever donated blood or perhaps hurt yourself and had to go to the emergency room and they sterilize needles, then you've used iodine because it disinfects and sterilizes. There's a commonality here. Kills bacteria that cause tooth decay. Chlorine is a disinfectant. Iodine sterilizes. So there's a pretty heavy-duty commonality in all these halogens. Let's take a look at one more. This is the very first group all the way to the left. It is called group 1. These are what we call the alkali metals. There are 6 that we commonly recognize. This is lithium. Obviously, we've heard of sodium before. The chemical symbol is a little different because it was named when it was still referred to in Latin as natrium. Here is the same thing with potassium. This is something called rubidium. This is something called cesium, and this is something called francium. And rather than showing you what it is that they do, or excuse me, rather than telling you what it is that they do, I thought I'd show you this neat video clip that does it better than I ever could. So let's take a look.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present.
Oh, thank you very much.
These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.
So, after watching that video, what do we come away with? Hopefully, you came away with one very obvious fact. Alkali metals react violently with water. And hopefully you also noticed that the severity of the reaction increased as we went from the top to the bottom. And did you notice how he said that they wouldn't give him any of this francium stuff? Anyone want to try to guess why that is? I'll tell you. Francium is radioactive, meaning it would be muy peligroso, very dangerous to throw that into water because it would spray radiation everywhere, and that it would be bad. So, a couple more things that we learned is that groups go down, periods go across. We know that group 1 are called the alkali metals. Group 18 are the noble gases. Group 17 are the halogens. Group 2 is something called the alkali earths, but we'll talk more about those later. Hopefully, we also noticed that elements in a group tend to react the same. Noble gases, for example, are all inert. Halogens are all toxic. And alkali metals all react violently with water. We'll worry about the alkali earths another time. A couple other things we want to pay attention to is that we're going to divide the periodic table up into two sections. They're not exactly halves. And we'll describe everything that exists on the left side as metals. They tend to have similar properties. They tend to be shiny. They tend to be malleable, meaning they are flexible, and they tend to be good conductors of electricity. Whoops, I should spell that correctly. Of both electricity and heat. Good examples of things that are metals are things that are metal-like. Gold is shiny, copper is shiny, silver is shiny, titanium is shiny. You get the idea. Elements that appear on the right side, we're going to call these. Let's use a different color. Let's make it thicker. Even thicker, so we can read it. We'll call these non-metals. These tend to exhibit properties that are very non-metal-like. They tend to be brittle if they are solids. Although, to be truthful, very few of them are solids. A lot of them are liquids, or in the case of the gases, gases. They also tend to be poor conductors of heat and electricity, and they tend to not really be shiny at all. All right. So that's our basic overview of the periodic table. It's kind of interesting, but we're going to stay away from all of these guys on the bottom for the moment, and we'll explain why as we go. All right. See you on the next one.